Okay, so now let's look at the non-homogeneous Euler-Cauchy equation. So, for example, the equation, if the equation is x square y prime, y double prime, this is the second order equation, minus 3 xy prime plus 3y is equal to 2x power 4 e power x. So this is a non-homogeneous Euler-Cauchy equation. So just like for non-homogeneous differential equation with constant coefficients, the solution of this equation will be also equal to the sum of the solution of its homogeneous part plus its particular solution. Okay, so for its homogeneous part, we will consider this equation x square y double prime minus 3xy prime plus 3y is equal to 0. And for this equation, since this is an Euler-Cauchy equation, we can find its characteristic equation as m square plus a minus 1. A is minus 3 minus 1 m plus b is 3. So its characteristic equation is m square minus 4m plus 3 is equal to 0. Which factorizes into m into minus 1, m minus 1, m minus 3 is equal to 0. So therefore m1 will be equal to 3, m2 will be equal to, m1 will be equal to 1, m2 will be equal to 3, and it will be a real distinct case. So homogeneous solution will be c1 e power x plus c2 e power 3x. It's not e, and now I'm making a mistake. Since this is an Euler-Cauchy equation, so it should be c1 x plus c2 x power x cube. Yes, so this is the homogeneous solution. Okay, homogeneous part solution. So for the non-homogeneous part, we can apply the method variation of parameters method, just like we did for the second order ordinary differential equations. For such a function over here, which is a little bit not of the order, although this function is it seems to be in a kind of standard form for the application of the method of undetermined coefficients, but we can, I think in this case it will be easier to apply the variation of parameters method. Variation of parameters method. So if you recall, for the variation of parameters methods, the particular solution is equal to minus y1 integral y2 and this function we call it as f of x, or whatever we can call r, whatever. Let's call it f of x, y2 f of x divided by Wronskian of y1 and y2 times dx plus y2 y1 f of x divided by Wronskian d of x. So if we want to apply this, then we need to calculate all these things. So we already know that y1 is x and y2 is x cube, okay, and f of x is yes, here I think we should be careful, whereas for the homogeneous solution we don't have to divide this equation by x square. For the variation of parameters method, because this method, variation of parameters method, takes x square as a coefficient, so this therefore the equation should be in the standard form for the variation of parameters method. Therefore, we will, for the application of this, we need to apply divided by x square. So in this case, if we will divide by x square, the function of x will be then 2x power 4 e power x divided by x square. So it will be 2x square e power x. Okay. So in this way, then the coefficient of y double prime term will be 1. And now we can apply the variation of parameters method. So calculate the Wronskian. Wronskian is x cube, then 1, and then 3x square. Then it will be 3x cube minus x cube. So it will be 2x cube. So that is the Wronskian. Okay. And now we can calculate yp. So yp will be then minus y1 minus x integral x cube fx was with this 2x square e power x divided by 2x cube, okay, dx, and plus x cube x, and then it will be 2x square e power x over 2x cube. Yes, so dx. So now we can just simplify it. Yp is equal to minus x integral. So in this case 2x cube, this cancels out, 2 cancels with 2x, x square, and then so the left is over here is x square ex dx, and then plus x cube, and here it is. So you can see that 2x cube cancel. Here it is only e power x dx. So the first term we can integrate by parts, or you can use the shortcut method, which I just explained before at the very beginning. The shortcut method is, you can take is di derivative. So you can take the derivative of x square and then integration of e power x repeatedly. So from x square we get 2x, then integration of e power x is ex, 2x is, then we get 2, then power ex, and then 0, and then e power x, and then for the sign will alternate plus minus plus. So very easily we can say that the integration this integration by parts will be then equal to x square times ex, x square times ex will be common, so it will be x square and then minus 2x and plus 2, right, times e power x, and then x cube, then here it will be just e power x. Okay, so now just simplify, make some simplification. So take this ex inside, so e power x, and then I take this minus x inside, so it will be minus x cube plus 2x square minus 2, and then it will be plus x cube. Okay, so x cube cancels with x cube, so what's remaining is e power x 2x square minus 2. So this is the particular solution. So we have just obtained the particular solution. So the total general solution will be then cx c1x plus c2x cube and plus 2 x square e power x, yeah, so it will be, for example, 2x square e power x minus 2x, sorry, 2 e power 2x e power x. So it will be let me see, I did a small mistake over here. It was x over here, and it should be x over here, so it should be 2x e power x. So this is the solution, c1x plus c2x cube plus 2x square e power x and minus 2x e power x. So this is the complete general solution. Okay, so this was the example for the Euler-Cauchy equation in the non-homogeneous case. So we can take one more example and let's see what we can do. Okay, so let's take one more example. X square y double prime minus xy prime plus y is equal to log of x. Well, this equation is a Euler-Cauchy equation, non-homogeneous equation. We can apply the variation of parameters method over here as well. However, in this variation of parameters methods, the integration will be a little bit complicated, so which can be done, but there is another simpler method, and that method is uses some substitution. So the substitution over here is that we assume that this function over here is is equal to t is equal to log of x. Okay, we assume t is equal to log of x, and then this will mean that e to the power t will be equal to x, so x will be equal to e to the power t. X will be equal to e to the power t. So in this case, we can say that we can see that t is a function of x. Yeah, or we can say that x is a function of t, and y is a function of x. So we can apply a chain rule. So if we take the dy over dt, dy over dt, dy over dx, if we differentiate dy with respect to x, then this will mean that it is equal to dy over dt times dt over dx. Okay, so if we can differentiate y with respect to t and d. So this equation simply says that if we want to take a derivative of y with respect to x, so what we can also take the derivative of y with respect to t, which in turn will be equal to the derivative of t with respect to x. Okay, so in this case, what we can see is that if we take dt over dx, so dt over dx will be equal to 1 over x, yeah, from this equation. So we can write it like dy over dt into 1 over x. So this is the first derivative y prime. Okay, the second derivative d2y over dt square will be equal to this will come, we will apply the product rule over here. So it means that dy over dt times the derivative of 1 over x square, which will be minus 1 over x square, and then plus this 1 over x times the second derivative of dy with respect to t. So that will be d2y over dt, and then t, derivative of t with respect to x. Okay, derivative of t with respect to f, dt over dx. Okay, so in this case, uh,